Hello and what's up to you all, Mindsetters? I hope you had a great day. My name is Abram and it is a lovely Tuesday, time for physical sciences. And you know, I'm with Tracy. Tracy, how are you?
I'm very well, thanks, Abram. And Mindsetters, it's good to be here and good to be talking physical science. So I really hope you've got your thinking caps on.
Awesome. And what are we doing today?
Today, Mindsetters, we're going to be looking at electrostatics. And this is a nice, again, foundational content. When we talk about electrostatics, we're talking about charges, electrostatic charges, so positive and negative charges, and you know opposite charges will attract each other, and all those kind of things. So we're going to be looking at electrostatics today.
Awesome. And well, let me tell the Mindsetters, if should they have any questions, we're here to help them, right?
Absolutely.
Of course. So all you need to do is to go to facebook.com/learnextra, like our page, share it with all your friends, your classmates, even your teachers, and tell them that they should go to Learn Extra and help one another on the page, because that's the spirit of Mindsetters. #work together. We want to be with you. Some of you are writing their test today, so let me know on Facebook how did you guys write. But also follow us on Twitter @Learn Extra. Last thing, we do have notes linked for you guys. They are all for free, guys. Free, mahala. Two options, the viewing option and the download option. I'll post them on Facebook. And the last thing is we have the test yourself links. 2 questions whereby if you answer them correctly, you stand a chance of winning this awesome Casio calculator, proudly sponsored by Casio. And the winner from last week's show will be announced later on the show. So Tracy, I see already the challenge question is up on the page, so do check it out, Mindsetters. Tracy will tell you more about it.
Absolutely. So today, as I said, we're going to be looking at electrostatics, and this is charges and conservation of charge. Very, very interesting stuff. So in this lesson, obviously we have to define electrostatic charge, and it's helpful that we consider charges. Also conservation of charges. And then always, you know, we are solving problems because we want to help you, Mindsetters, as you prepare for tests and exams. And science is so much about application, and you have to be practicing questions. You've got to know your theory, but practicing questions is the way you're going to really, really improve in your physical science. So, the challenge question for you today. The challenge question is about 2 students that are investigating electrostatic charge. So, Mike and Paul investigate electrostatics by rubbing a plastic bottle made of polypropylene on a silk scarf and another polypropylene bottle on Mike's hair. So they're playing around and they've got a scarf, and it's a silk scarf, and they rub the polypropylene bottle, and then they take another bottle also made of the same substance and they rub it against Mike's hair. And then they investigate what happens. What they find is that both objects are attracted to the object that they were initially rubbed with. Paul, her understanding of what's happening is that she suggests that both bottles have become negatively charged, while Mike argues that the bottle rubbed with the silk must have become positively charged and the other bottle must become negatively charged. So he thinks the one with the silk was rubbed with the silk was going to become positively charged and the other one negatively charged. The question is who is correct, because they've got 2 different explanations. Who is correct? Provide reasoning for your answer. And my hint to you is go and look at the Triboelectric Series. And then the second part of this question, suggest a way to prove who is correct. And by that what I'm meaning is in a practical manner. So if you now have these 2 bottles that are charged, how would you actually physically, practically go and work this out, that which of those 2 are correct? So you've got some thinking to do, Mindsetters, because I really, really want you to be applying this knowledge. As I said, science is all about application. Let's get straight into the theory, though, and do a bit of recap for those of you who are not sure. When we speak about electrostatics, we're speaking about charged objects, but we need to understand, what is matter made of? Remember a number of weeks ago, in the first term, we would have spoken about the atom. And the atom has got positives in the protons in the nucleus, with some neutrons as well possibly, but protons inside the nucleus, and around this nucleus spinning in regions of space called orbitals within energy levels, there will be electrons. So, in terms of where we get the positive charge would be coming from the protons, which are inside the nucleus, deep in the center of the atom. The negative charges would be found because we've got electrons spinning in those regions of space around the nucleus. So that is where we come with all positive and negative charges. Goes back to what substances are made of, and they're made of atoms. So, if the number of protons is the same as the number of electrons, the object is going to be neutral because there's no overall charge. So the substance could be neutral, overall objects could be neutral, or they could be charged. And I'm going to change color here. A charging could happen through the transfer of electrons. That usually happens through either contact with something that is charged, touches against something that is not charged and causes it to become charged, or by, like we had in the challenge question, by rubbing through friction, there is a transfer of electrons. And remember, I'm saying to you here, it's electrons that are transferred. The reason for this is that it's the electrons that are spinning around the outside. So the electrons are what are going to be transferred between objects. The protons, remember, the positive charges deep inside the atom, inside the nucleus. So specifically, it's the electrons that are transferred. So 3 cases that we could have. It is neutral, which would be same number of protons and electrons. If something is positively charged, and I'm going to do a big plus sign there, it means it's got less electrons than protons. Okay? The protons number is higher than the number of electrons. How would that have occurred? Well, electrons must have been lost or given away because electrons from the outside have been taken away, and so leaving behind more protons and less electrons. If something is negatively charged, then it's going to have an overall minus charge. It means it's got more electrons than protons. Extra electrons must have been taken in, gained. More electrons have been given to this thing, so it's now got more electrons than protons. Remember, it's the electrons that are transferred because they are on the outside. So, we've got neutral or positively or negatively charged. For example, how would you charge something? Well, I know certainly with my hair it's very fine. You can rub it with a balloon and my hair will go everywhere. Rubbing your hair with a balloon is an example of charging, causing a charge, electrons to be transferred, causing an overall charge. Discharging, so charging is building up charge. Discharging would be the opposite, when that excess charge is removed. And usually, it could happen, and particularly you might be experiencing this on winter's days, where the air is generally quite dry, and so as we walk around, we might experience, when you touch something, you get a little shock, maybe even a little spark. When you touch something usually metallic, which is a very good conductor, or even another person, any excess charge that you have collected is discharged. And so we've got charging, building up charge, or discharging that's excess charge being released. We often come across diagrams in this chapter, and specifically when you deal with diagrams, I've got a few points I want you to think about. Always. So I mean, imagine I've got a ruler and a plastic ruler and a silk scarf or a woolen jersey or something like that. Always when you're dealing with these different diagrams, make sure that you recognize what the charges were when they started. Okay? So that's a couple of points to note. We often are dealing with one object rubbed against another. Consider the following points. Check what the initial charge is of each object. It could be positive, it could be negative, or it could be neutral. Check what the original initial charge is at the start of each object. Positives would obviously be indicated with little plus signs, negative with little minus signs. Note that they're not showing you the total number of electrons, because if you imagine how many atoms are in a plastic ruler, thousands, millions. There are so many, but what we're going to be talking about is an overall balance. What is the net amount of the net amount, the overall amount of whether we've got more positives or more negatives. So note that the diagrams show the balance and the changes that are occurring. They are not showing the actual location or the actual position of positive and negative charges. Rather, we're trying to show just a quick general impression of whether this thing is now positively or negatively charged. The charges would of course be spread throughout the material, because if they are, say, the ruler is now negatively charged because we've rubbed it with something, it would then have extra electrons, and they're going to be repelling one another. So they're going to try and get as far away from each other as possible. And so if I show a couple of little minus signs on it, it's not showing the actual location of those extra electrons, because they would be spread across the whole material. Real changes would happen by increasing or decreasing the electrons, specifically at the surface of the materials. And then always keep in mind conservation of charge. So if, for example, you have gained an extra 5 electrons on the one, it would have lost 5 electrons on the other. Overall, no charge can be created or destroyed. So we've got to keep in mind conservation of charge, and that's critical. Let's talk a little bit more about conservation of charge. When we speak about conservation, we're speaking about keeping something the same. So if we're considering conservation of the rhinos, we must be thinking about, we want rhinos to be around for future generations. We want them still to be here. Okay? In the same way, when we speak about conservation of charge, charge cannot be created or destroyed. It must still be around at the end. Whatever you've done, it's still going to be around. It might be in a different place, but it's still going to be around. So charge is neither created or destroyed. It can only be transferred, given from one object to another. Remember, charge is measured in coulombs. That is the unit of charge, measured in coulombs. Each electron would have a charge of Q is equal to minus 1,6 times 10 to the negative 19 coulombs. Now that is a very tiny number, but if you think, how big is an electron? Very, very tiny. So negative 1,6 times 10 to the negative 19 coulombs is a very small number, but you've got lots and lots and lots and lots and lots of electrons. So each electron has that charge. The overall charge of an object will be, well, the total would be however many electrons you've got multiplied by the charge on each electron. So I've got this quick equation. Q, capital Q, is equal to the number of electrons multiplied by Q times E, the elementary charge, or the charge on one electron. And if you're dealing with protons, they would have exactly the same amount of charge, but it would be a positively charged, so plus 1.6 times 10 to the negative 19 coulombs. Conductors, by definition of the word, will allow charge to move through them easily, and so excess charge would spread evenly over the surface of spherical objects, recalling that they're trying to get as far away from each other as possible. Insulators, they don't allow charge to move, so do not allow charge to move through them easily. And then we'll deal with, very often, identical conducting spheres coming into contact and will share their charge. So imagine if I have 2 metal spheres and they're each on little wooden sticks, and I can bring them close together and move them apart. When they come together, that's now one object, one big object, okay? Because being metallic, they would be good conductors, and so would allow any excess charge to spread over the whole surface of that now much larger object. And then when I move them apart, they would spread or share their charge evenly. So we have a great equation. Q is equal to Q1 plus Q2 divided by 2. Because as you separate those charges, the total charge between them will be shared. And we're going to look at a couple of problems like that in a few moments. My hint to you is that, remember we said we're going to be dealing with 1 coulomb, or coulombs of charge. Coulomb is the unit of charge. But 1 coulomb of charge is a very, very big number. And so we are often dealing with much smaller quantities. So micro coulombs or nano coulombs, maybe even millicoulombs. Or, the important thing here is that you go and refresh your memory in terms of your prefixes. When I speak of microcoulombs, micro stands for, well, it's got that little symbol. Micro is equal to times 10 to the power of negative 6. And so if I've got 1 microcoulomb, it would be 1 times 10 to the negative 6 coulombs of charge. Nano would refer to, symbol N refers to times 10 to the power of negative 9. Go back and recap some of those prefixes. They will really help you in these following chapters. I think that's enough of a recap. We're going to come back to some questions. Abram, over to you.
Thank you so much, Tracy. And Mindsetters on the page, thank you so much. You guys are saying you're enjoying the show. And a big welcome back. Shout out to Nsovo Makam, who says, I really missed this show. That's Ayoba. A shout out to everyone. And also Olani saying, hi guys, I was 10 minutes early today. So thank you for being early on Alena. And Master K saying he hasn't been having a teacher for the past months. They didn't even write their first term physics, so he won't be able to join us. But I just said to him on Facebook, it is not an excuse to say that you didn't have a teacher. You can still push Mindset. It's up to you. Every obstacle that you come across, it is meant to teach you a lesson and to give you something. As Mindset, we have all the lessons from your term 1 up until this far. So get the notes, get the lessons on our YouTube channel, and we're here to help you. But otherwise, we'll see you after the break. Welcome back, Mindsetters. Now, as promised to you, that we have a competition that we're running through the Test Yourself questions. All you need to do is to click on the link that I'll provide on Facebook for the questions and then answer them correctly, and you could stand a chance of winning this awesome Casio calculator. Now, I have a winner from last week's show, and our winner is Mathiwo Mulambo. Mathiwo Mulambo, congratulations to you. Sorry, it's Mateo Mulambo, congratulations, you have won yourself this Casio calculator. Mindsetters, remember, if you have some questions, I'm here to assist you. We also have a help desk that is dedicated to help you guys. It's apps.facebook.com/learnextra help desk. I'll share that on Facebook, so do check that link, and the notes for today's show, they're very important because that's what Tracy is doing.
Fabulous, thank you. And Mindset is, I've got a little bit more of a summary in terms of Triboelectric Series, but I want to move on because the Triboelectric Series, I said to you, was the hint for your challenge question. So we'll come back to that a little later. As we go on to some questions now, we're going to be thinking about the fact that opposite charges will attract and like charges will repel, because opposite charges, positive and negative, will come together, and like charges will repel away. Try and get as far away from each other as possible. So we get this question: 2 insulated graphite-coated polystyrene spheres. Now let's just talk about what we have even from the question. When they say they're insulated, in this picture I can see they look like they're hanging on strings, which means they're not connected to the ground. They could be, and so they're not going to be earthed, which is important. So no charge is going to be moving away from them, all right? They're insulated, but they are coated in graphite, and graphite is a conductor. The polystyrene spheres are what's made, what the center is made of. So that polystyrene is an insulator. So the idea is that charge would be able to move around the outside because it's a conducting. Graphite is a good conductor, but it's insulated from its surroundings. They are suspended from threads. The spheres are held a distance apart. The charges on each of them are minus x coulombs, so a value, minus x, but it's a negative charge, and I'm going to put a little minus next to that, and positive 2x. So on that side, I'm putting a positive charge. Let's just actually undo that and make it a little bit further away so you don't think it's suddenly a different sphere. When the spheres are then released, what are they going to do? Well, they're going to move close to each other. Why? They tell us in the question that they do. When the spheres are released, they move towards each other. But why would they move towards each other? Well, the one is positive and the other is negative, so they're going to be attracting, and that's our first question. Explain why the spheres move towards each other when they're released. Well, important to notice, opposite charges, and maybe you could have their thought on positive, negative, will attract each other. The two spheres now touch each other. Calculate the charge on each sphere. So, when they come together, and I'm going to draw this as another little picture. Let's give ourselves a bit of space here. So, they were initially separate. Then they came together and they were touching. And then they moved apart again. Okay? So, here it was minus x, and this was positive 2x. Now they're going to come together, and the overall charge would be, well, overall would be minus x plus 2x, because the overall charge must be added together. Then they move apart, and that overall charge would be then split between the two of them. So, well, how would you work it out? Think this through, in that we would say when they've got to separate, the total charge, so I'm just writing Q1 plus Q2, must be divided over each of them, so divided in half. So I already have the total charge there. It was minus x plus 2x, and that whole thing must be divided by 2. Well, what is minus x plus 2x? That's going to be x, and it's divided by 2. So each of these spheres would contain x over 2, x over 2. Is that positive or is that negatively charged? Well, the x is positive, so it's definitely positive and another positive charge there. The question is, what's going to happen to them? Are they going to attract or are they going to repel? Well, let's go back to the question and think about it a little bit more. So, calculate the charge on each sphere. We just did that. X over 2. Maybe we could say the new charge on each sphere once they move apart. Will the force now be one of attraction or repulsion? Will they be attracting or repelling? They would repel. Why? Well, because they are like charges. Recall that we said they were both positive charges. So they're going to repel away from each other. And so how would you observe that? Well, the pieces of string, you would very clearly see lifting up as they're repelling, as trying to get as far away from each other as possible. The next one, will two charged spheres that touch always move away from each other? Explain your answer. Well, very likely they will, but will they always? The answer is no. What happens if I had two spheres and the one was negative x, and the other was positive x. So maybe negative 2 coulombs and positive 2 coulombs, for example. When they come together, the overall charge would be 0, and that would divide by 2 for each of them, and so there would be no net overall charge. So the answer here would be no. We would say if the net or overall charge is 0, there would be no repulsion. Because they can cancel out, but then there's no overall charge. So that would be an example. Next question. This is a relatively long question, but it's all about an experiment. So let's follow this together. Nazili and Layla perform an experiment to determine the charge on a metallic sphere. So metallic, and you're thinking it's a conductor. They proceed as follows. They attach the inflated balloon. So they've blown up this balloon, and they attach that balloon to one end of a wooden stick. Now the wooden stick is an insulator. The balloon is also an insulator. They charge the balloon negatively by rubbing it with a woolen cloth. And they obtain a metallic sphere mounted on an insulated stand. So this first picture, there's the metal sphere. And notice it's attached, the little side here, to the earth. It is mounted on an insulated stand, but then the sphere was earthed. Why must the sphere in figure A be earthed? Well, earthing is very important because earthing makes sure that when we start, that this metal sphere has no charge. It is completely neutral. So our answer there would be to ensure that the metal sphere is neutral. Earthing, in this case, allows any excess charge to move, or can we say flow. Therefore, we know that at the start it neutralizes the sphere. So the sphere, if it did have any excess charge, has no excess charge. It is completely neutral, and so we're starting with a neutral object. Next question. In figure B, the Earth is removed. So do you notice that little part on the side which was connected to the Earth? That's been taken away. The negatively charged balloon, so here's the balloon, and you notice the little negatives on it, is then brought close to the sphere. How will the charge be distributed on the sphere? Recalling that the sphere is metallic, and so therefore is a conductor. If it's a conductor, then it is going to allow electrons to move around it. So what's going to happen? Well, the electrons are going to try and get as far away from the electrons on the balloon as possible, because like charges repel. So the electrons are going to try and get as far away as possible, and so my answer here would be electrons on the sphere will be repelled. And so if they are repelled, they will move to the furthest side of the sphere. They're going to try and get as far away as possible. And what they're going to leave behind, well, the protons are locked in place, because remember, they're in the center of the nucleus. They're not allowed, they can't move. So leaving behind the positives would be all over, but more positives on this side in comparison to the negatives. And so protons would remain behind, let's say the leaving the side closest to the balloon positive. Remember, I'm just putting in brackets here, the protons are fixed. They can't move closer. Okay? They are locked inside the nucleus, and that's critically important. Next question. In figure C, the connection to the far end of the sphere is earthed. Oh, this is interesting. So now, remember what we had previously. We had little electrons were there. Now, this is earthed, because they tell us it is connected to the Earth. And so what's going to happen? Well, remember, we're saying electrons from the balloon are repelling the electrons on the metal sphere, and those metal ones on the metal sphere are going to try and get as far away as possible. And so how are they going to get there? Well, they're going to go down to the Earth. Do the negative charges move from the sphere to the Earth, or the other way around, from the Earth to the sphere? Well, definitely they're going to try and get as far away as possible, and so they will move from the sphere to the Earth, without a shadow of doubt. In figure D, the connection to the Earth is once again removed. What will be the charge on the sphere now? Well, recall from our previous step, the electrons scurried away as fast as possible. They were repelled, and so what's going to be left behind? Well, those protons are still fixed. And so the positive charge is left behind. What will be the charge on the sphere now? It will be positive. State whether the balloon will be attracted or repelled by the sphere. Well, what is the balloon? The balloon is negative, the sphere is positive, and like charges like charges repel, but we've got unlike charges here. So unlike charges attract, because the balloon was negative and the sphere was positive, so they're going to attract one another. Let's see, any more questions on this? I don't think so. That was E. I don't think so. But I want us to take another moment now. I want to just give you a hint on that Triboelectric series that I promised is coming up in the challenge question. So let's turn there together. I'm going to jump through. The Triboelectric series determines the charge when one material is rubbed with another. So it's a comparison table where you're going to be able to compare whether like charges or whether something's going to become positively or negatively charged. Which will become positive and which will become negative. Materials on the more positive end of the series are more likely to lose electrons, and so they are more likely to become positively charged because they're more likely to give away electrons. Materials on the more negative end will gain electrons, will take up extra electrons. And what does that mean? Well, then they're going to have more electrons than protons, and so therefore they would become negatively charged. So they become negative. Let's have a look at this one. Teflon is rubbed with some polyester cloth. So the first thing you need to do is go and find the two materials that you're working with. And the question, which will become positively and which will become negatively charged. So I'm going to go along to my table and search for, I see, was it polyester? Polyester, I see polyester over there. And Teflon over there. So Teflon is right down at the bottom, which the table is telling me is very negative, which means the Teflon will become negatively charged. And the polyester, which is higher up on the table, will become positively charged. So if the Teflon, I'm just going to write the positive sign, the Teflon will become negative and the polyester cloth will become positively charged if they are rubbed one against the other. Okay? And then when we deal with attraction and repulsion, we've talked about this already, unlike or opposite charges will attract one another, and like or the same charges will repel one another. This force of attraction or repulsion is always significantly stronger when the charges are close together, and they're significantly weaker when the charges are far apart. So the closer together they are, the stronger the force will be experienced by those. And you'll do electrostatics further as you go into grade 11 and grade 12. So it's very important that we lay the foundations now. So make sure that these things make sense. Abram, I think over to you. Work on your challenge question, mindsetters.
I like that, talking about preparation also and making things on time. Malcolm X once said that education is our passport to the future. For tomorrow belongs only to the people who prepare for it today. So it's all about preparation. Start preparing now and never ever waste any time. We'll see you after this break. Welcome back, mindsetters. Now, checking on Facebook, I see that some of you are confused there and there, but don't worry, we're here to help you through. Even on the challenge question, I see there's Team Mike and Team Paul. We'll see who's right and who's wrong when Tracy is answering the challenge question.
Brilliant. So we are onto the challenge question, and I know there was one or two questions on the challenge question. What was polypropylene? I think was asked. Who asked that?
It's Mpoentle Morotwa.
Well, importantly, I'm not going to get your name right, but
You just did.
Did I?
Yeah.
So I'm really well done for thinking about the challenge question. Polypropylene is a type of plastic. And you know, we have a number of different types of plastics or polymers, specifically that we can use. And polypropylene is a type of plastic. So that's why I specifically gave it to you as polypropylene, because I want you to be able to go and research, find it on your Triboelectric series and be able to work with that. So I hope that helps, but polypropylene is a type of plastic. Any other questions?
I think we can do them after the challenge question.
Should we tackle the challenge question next? So, Mike and Paul investigate electrostatics by rubbing a plastic bottle made of this polypropylene on a silk scarf and another polypropylene bottle on Mike's hair. So, I always give myself space, and I almost always do a sketch. The reason I do a sketch is because a picture says 1,000 words. It will really help you to interpret the question. And your sketch doesn't have to be beautiful, but it does have to include some information. So I'm going to start with a little plastic bottle. There's the lid. And it's not the best bottle in the plastic bottle, but it'll do, because all I want to see is that little bottle of water, and then let's do another one. See, and I'm just going to neaten that up slightly. Okay, So we've got two little bottles. I'm going to just show there's a little lid or screw cap on it. And they're both made of the same substance. So this one is polypropylene and also polypropylene. Then we take a scarf, and I've got a little yellow scarf here, and that is made of silk. That is what the question said. There are a silk scarf and another polypropylene bottle on Mike's hair. So let's do a little sketch. And that's his hair. There's Mike and his hair. Okay? Very quick, random, but it's going to help me because I want to be able to interpret what this question is asking. And we're going to treat each one separately because the one was rubbed on the scarf separately and the other one was rubbed on his hair separately. So we're going to tackle each of them. I said to you we needed to go look at the Tribo-electric series, and I did just give you a bit of a recap on it. Let's consider what we mean in terms of the Tribo-electric series. And I think I need to just jump back here and look at this table. This table goes from the top as the things that are become very positive, and right at the bottom, and I'm going to have to shift it down, the ones that become negatively charged. So we're doing a comparison. Things that when they're rubbed are more likely to become positive, when there are other things when they're rubbed, they're more likely to become negatively charged. Because it's about those electron transfer again. Are electrons more likely to be given away from the substance, or are electrons more likely to be taken up by the substance? And it's all about a comparison table. So when you have a look through these, we've got polypropylene, and is polypropylene here? Yes, it is. I see it right at the bottom. There it is, polypropylene. And we were rubbing it with silk in the one. So comparing this table, which side is closer to the negative edge on this table? The polypropylene. The polypropylene is closer to the negative. So in this case, in that comparison, it's going to become negative, and that one's going to become positively charged. The polypropylene is more likely to gain electrons, and the silk is more likely to lose electrons. So I'm going to go back to my table, or my picture that I drew, and once they've been rubbed, these are more likely to become negative. And let's change color so we can very clearly see. More likely to become positive. I'm going to just draw in the correct number because I had 2, 4, 6, 8 there, 2, 4, 6, 7, 8 there. Overall, my charge is conserved over the two, but definitely the bottle is going to become negatively charged and the silk scarf positively charged. Now let's compare our next scenario where we had the polypropylene bottle versus Mike's hair. So let's go across back to our table, and we need to go and find, well, polypropylene we already have. Polypropylene right down at the bottom here. I'm going to circle it in the green color because now I'm going to do the green color comparison with human hair. Do we find it? There it is. And so, zooting down to the bottom, which one will become positively and which one will become negatively charged? I hope you can see now that the polypropylene is still lower on the table, and so it's going to be negatively charged. In comparison, the human hair was closer to the positive side of this series, of this comparison table. So it's going to become positively charged. Let's go across to our picture and fill in that information. So the polypropylene was negative and Mike's hair was going to be positively charged. Okay, he looks like he's wearing a crown now. He's not. He's got he's got positively charged. His hair has been positively charged. So comparing them, again, we've got conservation of charge 2, 4, 6, 8, 2, 4, 6, 8, positives and 8 negatives. The idea is that that's just a quick representation for us so we can see the overall conservation of charge and we can compare the balance. Now let's consider who was right. Who was correct? Well, let's compare their statements. Mpho suggests that both bottles have become negatively charged. Do we agree with her? Yes, we do agree with her. So, Mpho is correct. Provide reasoning for your answer. Well, I think we have in our picture here, having a look at it in comparison to the Triboelectric series, the silk scarf will become positively charged. The human hair is also higher on the table than the polypropylene, will also become positively charged. So the polypropylene bottles will each become negatively charged. And that's based on the Triboelectric series. So definitely we have made use of that Triboelectric series, and I think you could explain your answer in terms of that and in terms of that picture. Suggest a way to prove who is correct. Well, having a look at it, this is what our prediction is based on the Triboelectric series. But what could you do to prove this? Well, you could attach each plastic bottle to a piece of string and hold them up, and if they were to come together, then the one must be positive and the one must be negative. What are these going to do? Surely the one should be, if they're both negatively charged, they should repel one another because like charges repel. So let's make a note in terms of answering this question. If we were to attach the bottles to some string or thread, and then allow them to swing freely. By freely, we're saying they're able to move. If they are both negative, they will repel. And so you could very clearly see if they're repelling, then Mpho is definitely correct. They would be moving away from one another, okay, because they have like charges. And let's just add that in, like charges. So, I hope that's really helped you, and I hope that's helped to recap the Triboelectric series. I know there was a question on that. Abram, are there any other questions?
Just quickly, based on that, before we take these questions, it's funny when the mindsetters are being asked who do they suggest is right, and then another mindsetter says, I think they both became negatively charged. And they asked for one person, right?
We did ask for one person because I want you to compare and think about and analyze their statements. It's helpful.
Okay, let's take their questions. Is it important to know? Okay. Is it important to know the Tribo-electric series?
You know, I would expect that in a test or an exam scenario that they could give you a Triboelectric series. And the reality is this Triboelectric series that we've got has got a series of substances. You could be given a whole different series of substances. So I wouldn't, you can ask your teacher, but I would certainly imagine that you need to be able to interpret a table and interpret a Triboelectric series as opposed to memorizing it off by heart.
Okay. Neo Masenya says, what does the word earthed mean? Hashtag confused.
Hashtag confused. Let's solve that problem for you. Earth means connected to the Earth. And because the Earth is such a very large object, I mean, if you imagine, it's massive, the overall, the Earth can neutralize things because any excess charge will be able to flow towards the Earth or back to the object from the Earth. So it helps to neutralize any charged substances. So when we say earthed, we mean connected to the Earth so that excess charge can flow.
All right. James is excited about that. The man up says that we are all earthed because we are connected to the world.
Absolutely.
Last question. How can you define induction?
How can we define induction? Induction, a little bit challenging. When we induce a charge, we cause a charge to be there. We can induce the charge. So we can kind of cause a charge to be there. I think that's all from me. Mindset is keep thinking, keep working hard, and remember, practice as many questions as you can get your hands on.
Thank you so much, Tracy. We're closing it with a note from Noah saying, I love this channel, but most importantly, I love the people who are teaching and what they are teaching us. Thank you so much, Noah, and thank you so much, Tracy.
Thank you so much, Mindsetters, and I really hope today has helped you. From me, signing off, keep well and God bless.
Awesome. Thanks to you, Mindsetters, for watching. We love you, and we'll always be here for you guys. Peace.